Yeah, we have to do that too. Yeah, it's so painful.
So hard.
It's so exercise.
It looks really hard. I'm like, guys.
Lots of outside noise. Okay. All right, ladies and gentlemen, if I could have your attention back up here as we begin to review Chapter 2. Chapter 2 was the first time that we were introduced to function notation, which looked like what you see here. Given g of x equals x squared plus 3, let's see if we can remember what to do. What should we do if we're asked to find g of a? Plug in a in for x. Awesome, for function g. So we'll just plug in a and then we simplify, which there's nothing that this can really simplify to, so it's just a squared plus 3. Letter B, what are we going to plug in for x of function g? Rachel? I do. A plus h, awesome. So we're going to plug in a plus h in for x. But now this one, we can simplify a plus h squared. That turns into a squared plus 2ah plus h squared plus 3. So that would be the answer. Again, this is going to be multiple choice on the final. So this would be the answer you would look for. The one prior would not be there because this could be simplified. Josh? Yeah. All right, letter C. Then we took outputs and combined them together. So we're asked to take g of a plus h's output minus g of a and divide it by h. So we're going to take g of a plus h, which we found to be this. We'll copy that down. A squared plus 2ah plus h squared plus 3. And then I have to subtract a squared plus 3. Should I put that in parentheses? Does it even matter? It does matter. It matters because if I forget, I might also forget that there's a distributive property that needs to be used here. And this is all being divided by h. So now I simplify. I'll distribute that negative, and that becomes a squared plus 2ah plus h squared plus 3 minus a squared minus 3 all over h. There's a few pieces that cancel here. 3 and negative 3 cancel. A squared and negative a squared. So would my answer just be 2ah plus h squared over h? No. What can I take out? H. Good. If I factor the h away from those two terms, I'll have 2a plus h in parentheses all over h. We know that we can cancel out factors, so those guys reduce, and we end up with 2a plus h. All right, on to another concept we learned in chapter 2. After you understood function notation, you could understand function composition, which was where you had a function inside of a function. Do you guys remember which one was the inside function, f or g? G, good, because it was closest to the number. In fact, you could have rewritten this as f of g of 4. Essentially, it means you're taking the output for function g when you plug in 4 and plugging it into function f. So I'm going to want to evaluate what is g of 4. Take the square root of 4, and g of 4's answer is 2. And then we plug that in for function f, and I determine the answer. So I would have 2 squared minus 3 times 2 plus 2. 2 squared is 4, so I have 4 minus 6 plus 2, and negative 2 plus 2 gives me 0. So the answer to f of g of 4 is equal to 0. One thing to make sure that you make note of, this little O symbol does not mean multiply. Not multiply. That's a common mistake that typically occurs when we first see the symbol because it looks like the time symbol, but because it has a little space inside, it's represented as of, or something inside of something. All right, letter B. Evaluate f of g of x and state the domain. It's been a while since we talked about function composition domain. So I'm going to give you 3 steps off to the side of how you evaluate function composition domain. Do you still need that, Jen?
No.
Okay, so in finding f of g of x domain, there's really 3 things that you have to take into consideration. Number 1, you need to determine the domain of the inside function. So what would be the inside function if we're doing f of g of x? G of x. So if I look at g of x, which is equal to the square root of x, my computer froze on me, so just 1 second, it'll come back on in a moment. Zoop, there we go. What'd you say? I don't know why, but towards the end of the year, this one just constantly goes in and out. Maybe it's because I'm making it do so much. Daniel, you caught me. I keep so many things open. I have to close so many things. And I never shut down my computer at the end of the day, and I need to.
It feels like if you shut it down, don't you like lose all your tabs?
Not if I take the time to close them. But usually what I do is at the end of the day, I gotta go get my son from the grammar school. Close that, run, and then 1,000 things left
You know,
open.
like,
So
you know the thing with Google, how you can group the tabs now?
no, I don't know this. What do you do?
So basically, you can just like right click on it and you can add a tab to a group and you can group it by.
Well,
You'll have to show me that when we get downtime.
It's
I
a
don't
lot
know.
easier. I did that and it keeps and you can it's like you can close the group and you can open the group. and
Good,
the tabs
thanks.
Oh man, I'm gonna have to learn that. I'm totally gonna learn that. All right, guys. So quick reminder of domain. Domain is all the real number values of x that you can use to produce real number outputs of y. So if I look at g of x, what can you not have the square root of? Negative. So if I'm thinking about the domain, x has to be greater than or equal to 0. Or what if this was listed in interval notation? Would I have a bracket around 0 or parentheses? Bracket. Good. Okay, so that would be the inside domain. Step 2 is you determine the resulting domain. So I'm going to have to determine the domain of f of g of x. So now I actually have to perform this operation and determine what is f of g of x. So let's go back and start doing some math on this. F of g of x is the exact same thing as taking f of g's output. So if I'm looking at what is g's output, that is square root of x. So I'm going to go ahead and put that in for function f. So I'm asking what is f when I put in square root of x. And putting that in for x of function f would be the square root of x squared minus 3 times the square root of x plus 2. What happens when you take the square root of x and you square it? Good, the square root disappears, so it just becomes x minus 3 root x plus 2. So this is my answer for f of g of x. In fact, if I did this first, I could have just plugged in 4 for x and determined it would come out to be 0. But either of those are good. So here's my answer, but I need to determine the domain. So if I look at what is f of g of x, it's this. What would be the domain of that? Yeah, it's the same in this case because we have a square root again. And so again, x has to be greater than or equal to 0, or you could say 0 to infinity. Now, step 3 the actual domain, the domain is the overlap of 1 and 2. So it's going to be the overlap of this and this. Now this one works out pretty nicely because if I tried to graph 0 to infinity and 0 to infinity, they would overlap in the same location. 0 to infinity and 0 to infinity obviously are going to overlap in the same place. But I would want to be looking for where do those two intersect, and that would be what a composite functions domain would look like. So for f of g of x, I would say this would be the function such that its domain is from 0 to infinity. And that would be my answer.
How do you find a domain if it's not a root? Like a square?
If it's not a root, so you want to look at some more domains.
Yeah, I mean, so
If I had something like g of x equals 2 over x, do you guys remember what we can't have? You can't have a 0 in the denominator, right? So here, x just couldn't equal 0. So our domain would look like everything from negative infinity to 0, union with 0 to infinity. Those are the two main places to look for domain, to look for restrictions, is if,
it could be negative infinity.
right. So that's another example of a domain situation. Or let's say that I have h of x is equal to 2 over x squared minus 4. Then I would say x squared or x plus 2 times x minus 2 can't equal 0. So x couldn't equal negative 2 or 2. These are just some additional examples of domains. All right, and we're going to do another domain example actually further down in chapter 2. Okay, aside from function notation, you have to know how to read function notation with a graph. One thing that was actually supposed to get copied here, but it didn't, it actually kind of got shifted. If you could bold in this point and call it at 1, 1, and bold in this point, 6, I think it's at 8, 6. Yeah, and call it at 8, 6. That's going to be important for one of the questions. All right, number 3. What is larger, f at 3 or g at 3? Why don't you turn to your partner and answer this one together? All right, I heard it almost unanimously. F at 3, because it's above function g. Its y value is bigger. Find the values of x for which f of x equals g of x. So now we're looking here, here, and here. Those are 3 specific locations. What are the values of x? 2, I think it's 2, 3, 4, 2, 5. 2, 5, and 7. Awesome. But we just say x equals. How about the values of x for which function f are less than function g? So again, you're answering for x. I would have the answer in interval notation on the final, but we're looking for where is function f less than function g. Go ahead, turn to your partner, see if you guys can answer this one together. So Karis, this looks like it starts at the x value of 1, and then this one goes to 2. But since I'm looking for less than, it would be bracket 1 to 2 with a parentheses. And then I can join the other location, which would be 3, 4, 5, 5 to 7.
1 to 2.
Does that make sense?
I used, I don't know, I used.
All right, guys, go ahead and take a look. You should have bracket 1, 2 parentheses, union with parentheses 5 to 7. Wilbur.
Why aren't there brackets null?
Why aren't there brackets in all of them? Good question. Because the question didn't say where are they less than or equal to, they're actually equal to the functions at those 3 locations. So it's only less than everything with, it's definitely less than down here. So that's why I have a bracket at 1. but then I have to put a parenthesis showing that it's not actually less than g at 2. It's actually equal to 2, so I'm going to put a parenthesis there. All right, letter D, find the average rate of change. Ooh. Do you guys remember what average rate of change? What'd you say, Michelle? Slope. Good. That's just the slope. Between the points shown on function f. So that's why I had you bold in those points. It's supposed to be between the points 1, 1 and 8, 6. So now that we reviewed that average rate of change just means slope, we're looking at change in y over change in x. So that would be 6 minus 1 over 8 minus 1. The average rate of change would be 5 over 7. All right, on to another question. This was actually taken from your chapter 2 test. Given the new equation, y equals square root of 25 minus x squared, answer the following. What is the domain of the function? So again, we have a value underneath the square root. What can you not take the square root of? Negative. So if I'm solving for x, I would say 25 minus x squared has to be greater than or equal to 0. As I'm looking at what x values would produce real number y values, I see that this is a quadratic. We call this nonlinear inequalities. Do you guys remember how to solve those? You do not add x squared to the other side. Do you guys remember?
25.
Or
Over?
do you kind of like distribute x minus 5 and x plus 5?
So close. So it's just, in this case, going to be 5 minus x, 5 plus x. But you're right, we have to factor it because Wilbur's using that rule, a squared minus b squared factors down into a minus b, a plus b. So a squared is represented as 25. Awesome, that's the first step. And then do you guys remember what we do with a number line to help us determine this domain?
Yes.
What do we plot on the number line? 5 and negative 5, because if I'm looking at what would make this parentheses equal 0, 5 minus 5 would give me 0. So 5 is a 0 value. It's going to help me gauge the answers on this number line. And negative 5 would make that parentheses equal 0. Then we just have to test the entire real number line to see what would make this greater than or equal to 0. So I would test a number to the left of negative 5, like negative 6. 5 minus negative 6 would create 11. 5 plus negative 6 creates a negative 1, and that is not greater than or equal to 0, so nothing works on this part of the number line. In the middle, we would test a number in between. I think 0 is the easiest. 5 minus 0 is 5. 5 plus 0 is 5. That is greater than or equal to 0. So that means everything in here works. And then if I test a number to the right of 5, like 6, I would have 5 minus 6 is a negative, 5 plus 6 is a positive. That is not greater than or equal to 0, so nothing works here. So my domain for this function includes everything from negative 5 to 5. Be my answer. Okay, is this function even, odd, or neither? Ooh, do you guys remember what an even function looks like?
Is it like, like this?
Something has to do, it has something to do with the x or the y-axis. I'll give you an example of an even function. Y equals x squared.
Even the number of places it crosses
The x-axis, if it's even, it means that it's symmetrical about the x-axis.
Wait, so odd is like kind of like.
Odd is like a cubic. It means that
Yeah.
it's symmetric about the origin. So to test if something's even, any xy function that works for the original function will have a corresponding negative xy that will also work for the original function. So we just test, really, we test negative xy and see, do we get back the same function? So if I look back at my function, which is y equals the square root of 25 minus x squared, I'm going to plug in really just negative x in for x and see, do I get back that same function? Let's see here, I have y is equal to, I'd like to do a question mark, the square root of 25 minus negative x squared. What happens when you square a negative? Becomes positive. So do we get back the same function? Yes, it's the same. Therefore, this is an even function. Do you guys remember what odd functions look like?
They're not symmetrical.
They're not symmetrical about the x-axis. It's actually symmetrical about the origin. So any xy will have a corresponding negative x, negative y. If you didn't remember that test, you might want to retry page 269, 73 to 74 in your book. All right, now that we know that this function is indeed even, we can build an xy chart to help us determine what will this shape look like. So here's my equation. Y is equal to the square root of 25 minus x squared. I'm going to use an xy chart, but I know that my domain, so the values that I can use for x, go from -5 to 5. In fact, if I just plug in numbers from 0 to 5, any points that I get to the right of the x-axis, I can reflect it to the left of the x-axis because I know this is an even function. So let's start plugging in a number like 0. The square root of 25 minus 0 squared, the square root of 25 is just 5. So I can plot the point 0, 5. If I reflect it, it's only at -0, 5, so that doesn't help me for that specific point. What would be another good number to plug in that would allow me to work through it? 3 is a good one. Work through it nicely. If I do 25 minus 3 squared, 25 minus 9 is 16. What's the square root of 16? 4. So that's a nice one. I can plot 3, 4. And since this function is even, I know that -3, 4 also exists. And then another good point to plug in would be 5. Because if I plug in 5, I have 25 minus 5 squared. 25 minus 25 is 0. So I have the point 5, 0, which I know because the function's even will reflect to -5, 0. You could have also plugged in 4 and you'd get out 3. But after we plug in more, well, really those points, I know that the function's going to go through these points and it's going to be reflective over the x-axis. All right, of those types of questions, 3 to 5 will be chosen from chapter 2 to go on the final. On to chapter 3. Chapter 3, use the equations below to answer numbers 1 through 4. Which of the equations above match each graph below? Let's go through each equation individually and think about what we know from chapter 3. If the equation has an odd degree, that tells you the end behavior. Do you guys remember if it's an odd degree, if it's going to go in opposite ends or the same ends? Good, opposite ends. It's either going to be up, down, or it's going to be down, up, but the leading coefficient will tell you. So if the leading coefficient is negative, then which direction does it go? Down, up, or up, down? Up, down. The easiest one for me to remember, I like to think of y equals x cubed, because I know that one, and that one always goes, that goes like this. So the behavior starts down, ends up, and that's a positive x cubed. That's easiest for me to remember. So negative x cubed flips it upside down. All right, letter B then. Again, it's an odd degree, so it's going to have opposite ends. But since this one has a positive leading coefficient, how is the end behavior going to go? Down, up. Letter C, this is an even degree. Even degree, yep, have the same end behavior, and you guys even remember how. So since it's a negative leading coefficient, I heard it, they're both going down. And for this last one, letter D, again, it's an even degree, so it's going to have the same end behavior, but since it's a positive leading coefficient, how do they both go? Up, up. Okay, use that to help you answer questions 1 through 4. Okay, you should have in order C, B, D, A. The other thing to be aware of, these equations came to you in standard form. Standard form means that everything's been multiplied out and all like terms are combined. Standard form determines end behavior. So then the question then arises, what happens if the polynomial is given to you in factored form, like the next one? You have to envision when you're looking for the end behavior, what would this look like if it was multiplied out? Essentially, what would be the highest exponent or the degree? Wilbur? Close. I do have 2. Well, I do have 2, I do have 3, but I have x to the first as well.
Oh, yeah.
Good. So this is going to be a degree 6. Do we remember how to find the zeros of this function? Hopefully we remember that. We've been doing a lot with zeros. Essentially, you set each of the factors equal to 0 and solve. So we get x is equal to -1, x is equal to 2, and x is equal to 0. So my zeros are at 0, 2, and -1. You guys answered. The degree of the polynomial is 6. What would the end behavior be then? Do we have a positive leading coefficient or a negative? Positive. So how are the ends going to face? Up, up. Awesome. So let's go ahead and plot those zeros. 0, 2, -1, and it's going to end up and up. Now, to finish the graph, there's something that we learned about the exponents of the factors. So if I have an exponent of 3, for example, that's going to tell me something about the 0 value, x equals -1. Do we remember a little bit?
It either goes through or it bounces off.
Awesome. Do you guys remember if it's an odd? Good. If it's odd, it's going to pass through at the 0. And if it's even, it's going to bounce. And then x to the first again is odd, so it's going to again pass through. So as I start completing these pieces, -1 is going to pass through, 0 is going to pass through, but at x equals 2, it's going to bounce. And there's a sketch. All right, let's see if we can do this critical thinking question. Here it is. Solve the inequality. X times x minus 2 squared times x plus 1 cubed has to be less than 0. Remember, when you're solving, you're asking what are the answers for x. Let me see if I can give you a hint. You just graphed this for y. So where is this function less than 0? Raise your hand if you think you know. Daniel.
Parentheses, -1, 0, parentheses.
Nice. If you look at the graph from -1 to 0, the function falls below the y value of 0. So along those x values, the function is less than 0. Nice. All right, chapter 3, we also learned for number 6, how to use the process of long division. You guys remember this? No? I think you'll remember it after a quick review. You can do this. Okay, first you check for any missing terms. There are no missing terms here. So then I'm going to put the large or the first number underneath the divide sign. So I have 4x to the 4th minus 2x cubed plus 4x squared minus 3x plus 1. And I'm taking that and dividing it by my divisor, 2x plus 1. And do you guys remember what we do first?
You put the first.
You divide. Okay, there's.
Oh, wait.
Divide the first term by the first term. So I could say, what's 4x to the 4th divided by 2x? What would that be?
2x cubed.
2x cubed. Or you could ask what times 2x would give you 4x to the 4th. Then you distribute back through. So that gives me 4x to the 4th plus 2x cubed. But then what do I have to do in the process of long division? Subtract. And I want to make sure that I subtract both terms. So essentially we want to distribute that in. The first two terms cancel, but negative 2x cubed plus negative 2x cubed is negative 4x cubed. And then we bring down the 4x squared, and the process starts over. What times 2x would give me a negative 4x cubed? Good, negative 2x squared. Distribute that back through, so I get negative 4x cubed minus 2x squared. And I have to distribute the negative, so that'll make this positive and this positive. The first two cancel. 4x squared plus 2x squared gives me 6x squared. Bring down the next term, negative 3x. And the process continues. What times 2x gives me 6x squared? 3x. I distribute back through, so 3x times 2x is 6x squared. 3x times 1 is 3x. And then I distribute a negative, negative, negative. Those cancel. Negative 3x plus negative 3x is negative 6x. Bring down the 1. What times 2x gives me negative 3x? Negative 3, distribute that back through, so I get negative 6x minus 3. Subtract, subtract. And so my remainder is 4. But I do want to be careful of how the question asks me to write the remainder. It says, put it in the form where you have your quotient plus your remainder over your divisor. So my answer would be 2x cubed minus 2x squared plus 3x minus 3 plus my remainder, which is 4, over my divisor, which is 2x plus 1.
And so on the test, we have like a scrap piece of paper.
So it will be Scantron, so you can write all over the test however you need, but then you just want to transfer your answers to the Scantron. All right, number 7, write the function in completely factored form, given that x equals 2 is a 0. One thing you want to recall that if x equals 2 is a 0, so I'll say if x equals 2 is a 0, then you know that x minus 2 is a factor of the function. If x equals 2 is a 0, then x minus 2 is a factor. Which means if I'm given a 0, I can take this function, 2x cubed plus x squared minus 13x plus 6, and divide it by x minus 2 to start factoring it down. Now, in the previous problem, we used long division. In this problem, we could actually use synthetic division. Do you guys remember how we do synthetic division?
We line up the coefficients.
We line up the coefficients, and what do we put in the little box? The 0, good. So we're going to put 2. And then we line up the coefficients, 2, 1, negative 13, and 6. Do you remember what we do with the first number?
Yeah.
Bring it down, good. 2 times 2, and then we multiply, of course. Multiply. So 2 times 2 gives me 4. 1 plus 4 gives me 5. 2 times 5 gives me 10. Negative 13 plus 10 gives me negative 3. 2 times negative 3 gives me negative 6. 6 plus negative 6 gives me 0. Now, do you remember what these numbers are if I took 2x cubed and divided it by x?
Wouldn't that be 2x squared?
Good. So that means this is going to be 2x squared plus 5x minus 3. That's another factor of this polynomial. So I could right now say that x minus 2 times this is equal to 2x cubed plus x squared minus 13x plus 6. Did I fully factor the function? No, what do I got to do with this guy? Yeah, factor it down. So the last term's negative, so I know I'm going to have different signs. 2x times x gives me 2x squared. And I'm actually going to have to make the 3 positive and the 1 negative. And then it adds up to that 5x. So my function fully factored looks like that. X minus 2 times 2x minus 1 times x plus 3. And last but not least in we still have a few more. But I was thinking we were graphing rational functions, but there's one other one that we need to look at, one of the rules from chapter 3. Which of the following correctly lists the possible rational roots for the function? Do you guys remember the rational root theorem?
It's something to do with like the
Factors. Yes, all the roots is equal to the factors of the constant divided by factors of the leading coefficient. So if you're finding all the possible rational roots for this function, which one's the constant? 4, good. So if I'm looking at factors of 4, that would include plus or minus 4 times plus or minus 1, and plus or minus 2 times plus or minus 2. The leading coefficient, what would be the leading coefficient of this function? 3. So I'm going to divide this by plus or minus 3 and plus or minus 1. And I need to look at all the different combinations. So I'll start with a denominator of 3. I know that plus or minus 4 over 3 are 2 possible rational roots. Plus or minus 1/3, plus or minus 2/3. Now I look at denominators of 1, so plus or minus 4, plus or minus 1, or plus or minus 2. What would be the answer then that lines up with all those possible rational roots? What do you guys think? These are our answers. What does that match in A through D? B. Letter B. All right, last thing to review. Evan? Yes. The last thing to review are horizontal asymptotes, vertical asymptotes, and holes for rational functions. So it says for questions 10 through 13, match the following description with the function. You will use each description only once. Do you guys remember how we determine what the horizontal asymptote will be for a rational function? There were 3 cases. Case 1 is if the degree of the numerator equals that of the denominator. I like to look at examples. So example, if we have something like y equals 2x squared over 3x squared, do you guys remember what the horizontal asymptote would be there? The degrees are the
This
same.
must be y equals 2.
2/3, good. It's the ratio of A to B. So if the degree of the numerator equals the denominator, then you have a horizontal asymptote at y equals A over B. Case number 2, if the degree of the numerator is less than the denominator. So example, if I have something like y equals 2x over 3x squared, do you guys remember what the horizontal asymptote is at? Y equals,
3, right? Is it the top or the bottom?
if the top one is less than the bottom. 0. Good. Y equals 0. And lastly, case number 3. If the degree of the numerator is greater than that of the denominator. Example, one of these would look like y equals 2x squared over 3x. Then there is none. So those are the 3 cases, y equals A over B, y equals 0, or none. All right, let's take a look, see if we can answer this first part about letter A then. Looking at the functions, which one has a horizontal asymptote at y equals -2? Well, which one do the degrees match, the numerator and the denominator? The first one, number 10, x squared and x squared. So the horizontal asymptote is -2 over 1. So number 10 would be letter A. Speaking of horizontal asymptotes, do you guys remember how we identify vertical asymptotes? They don't come from the top. It's from the bottom. You look at what would make the denominator equal 0. So this one would be -2 would make that denominator equal 0. So that would be your vertical asymptote. So that would be letter C. Speaking of vertical asymptotes, do you guys know how to distinguish between a whole? It has to do with the top. It's actually what piece cancels. So if I look at number 13, x squared minus 4, does that factor?
Yeah.
X plus 2, x minus 2, right? Since the x plus 2 cancels, what does that mean about when x is -2? It's a whole. So this one has to be letter D. And then number 12 obviously has to be letter B. But remember, your x-intercept is always where y equals 0. So if I set this function equal to 0 and solve, I don't have to worry about the denominator because the denominator can't equal 0. So if I look at where does 0 equal x cubed plus 8, it'll be at the location -2, 0. Okay, that was a quick review. See if with your partner you can do number 18, graph a rational function using those pieces. What did you say? Oh no, mine does that all the time. All right, Karis, are you starting with factoring the numerator and the denominator? So did you get x minus 5 times x plus 3?
Yeah.
Okay, and then the denominator, did you get x plus 3 times x minus 2?
Yep.
Awesome. So does this graph have a hole?
Yeah, x equals -3, right?
Yep. And then do you remember how to find the y coordinate of the hole?
I don't think so.
So we gotta plug it into what's left of the function, and that will tell us what's the y.
Oh, okay.
So if I do -3 minus 5 over -3 minus 2, that's -8 over -5. So 8/5, or we could say 1 3/5.
Okay.
And then the x-intercept is always where y equals 0. So I can take the reduced function, so take x minus 5 over x minus 2 and set it equal to 0.
Mm-hmm.
And then I could multiply both sides out by x minus 2. So I'm really looking for where does 0 equal x minus 5. And so x has to equal 5. So 5, 0 is the x-intercept. And if I'm looking for the y-intercept, that's where x equals 0. So using my function, I can plug in 0 for x. And I have 0 minus 5 over 0 minus 2, which is 5 halves. So I have the point 0, 5 halves, or 2.5. And then, Karis, do you remember how we find the vertical asymptotes?
That's where you set it equal.
0. So x equals 2 will be a vertical asymptote. And then we reviewed the horizontal asymptotes. Do you know what the horizontal asymptote would be for this function? So the degrees are the same. The degree of the numerator matches that of the denominator. So this one would be case number 1.
How do you find the graph crosses?
So it'd be a over b. So we have coefficients of 1 and 1. So do you remember what it would be?
What would you give?
It would be 1.
Yeah, y equals 1. And then to determine if the graph crosses the horizontal asymptote, we set the equation equal to it. So I'm going to take y equals x minus 5 over x minus 2. And I'm going to see, can it ever equal 1? If it can, then it'll cross. So I multiply this side by x minus 2 and x minus 2. And we get x minus 2 is equal to x minus 5, which can't work because -2 can't equal -5. So no, it does not. And then we graph the vertical asymptote, which looks like this. And we graph the horizontal asymptote, which looks like this. We plot the x-intercept, 1, 2, 3, 4, which is at 5, 0. The y-intercept, which is at 0, 2.5. The whole, which is at -3, 1 and 3, 1 and 3/5. And then the graph always goes through any points that you found and gets close to, but never reaches the asymptotes. And it gets close to, but never reaches the asymptote.
How do you find the vertical asymptotes again?
It's whatever in the denominator, whatever makes the denominator equal to 0 that didn't cancel. So since I factored x minus 2, x equals 2 would make the denominator equal 0. All right, guys, this is the graph. You guys have your test chapters 2 and 3. I would revisit those and then decide which book problems you want to try for tonight and tomorrow night. Only 10 are required. For the last 20 minutes of class, I'm going to have you work through chapters 8 and 9 with a partner. You do not have to finish it in class today. Whatever we don't finish, we're going to start with class on Friday. I'm going to give you guys time to finish 8 and 9 with a partner, and then we'll check your answers, and then we'll review chapters 4 and 5. And then that's it. Wait.
Are the formulas for 8 and 9 going to be on?
Yes, the same way that they're given to you here is how they will be given to you on the final. Johnny.
Can you go back to the 18?
Yeah. Actually, speaking of, before you guys start working with your partner, any questions on number 18?
Yes. What did you find? The whole-
The whole?
Yeah.
So the whole, we know it's at -3 because that's what canceled. To determine the y location, you plug in -3 in for what's left of the function. So when I canceled out x plus 3, I had x minus 5 over x minus 2. And so I plug -3 in for x, and -3 minus 5 gives me -8. And -3 minus 2 gives me -5. Evan? So to determine if it crosses the horizontal asymptote, you take your reduced function, which is y equals x minus 5 over x minus 2, and we set that equation equal to the value of the horizontal asymptote, which is 1. So we're going to see, can this equation equal 1? And then we solve, and we find that it actually can't equal 1, so it's never going to cross. All right, you guys have 20 minutes to re-engage in chapters 8 and 9. Hopefully that will feel freshest in your mind and you'll soar through, but go ahead and start working through with your partner. Karis, do you